to the homework right quick, and we should be able to get through this pretty quickly. Apparently my other window got closed. Hopefully the internet works today. Okay. Try and then again. Okay, there we are. Statistical methods. Homework and tests. Well, we want to go to 4. All right, let's go to about number 8 or so. See what happens. So we kind of need to get through homework 4 all today, because that way we can just review for the test. So everybody does remember we have a test on Friday. So if you can't come on Friday, make sure to make it to my office hours sometime this week, so you can take the test early. And yeah, okay. Okay, so here's data table. Let me open an Excel. So the first thing it asks us, hey, is this a probability distribution? How do we tell if it's a probability distribution? Yeah, they all have to be positive, which they are, and they all have to add up to 1. So I'm just going to go here and hit equals the sum, and see what we get. Yep, they add up to 1. All right, find its mean and standard deviation. How do I go about finding the mean? Well, I can't do average anymore because the probabilities aren't even. So I actually have to tell Excel what to do, right? So remember, you go each number times its probability first. So I say equals the number times its probability. Right? I do that all the way down. Well, I went down too far, but yeah. All right. Okay, I did all the number times its probability, and then the mean, remember, that symbol means add up. So you add up all the numbers times their probabilities. Let's go back here and say, okay, sum of all these. And it just wants a 10. All right, what about for standard deviation? So again, to get the variance, you go each guy minus the mean and then squared times the probability. All right, and so standard deviation, you're going to do that, but you're going to take the square root at the end. So first thing I need to do, I need to go, okay, each guy minus the mean squared times its probability. Okay, so I go my value. Oops, oh, sorry. I have to put an equal sign. So my value minus the mean, which I don't want this guy to move when I drag down. How do I keep him from moving? Yeah, you put dollar signs on it. Squared times the probability. And do that all the way down. And then the variance is just add those up. Okay. And then standard deviation is going to be what? Square root. So again, to get that variance, just some last column. And then to get the standard deviation, just square root the variance. All right. And this is also nearest tenth. So it's going to just become 1.4. And use the range rule of thumb to find the usual values for bumper stickers. So I'm not 100% sure this is what they're asking for. Let me actually try it first. Yeah. So the usual rule of thumb is that the most you're going to see is 2 standard deviations away from the mean. So one standard deviation is 1.4, so 2 of them is 2.8. So if I go mean plus 2.8, that's where I got the 3.3. And then for the minimum, well, it should be 0 because 0.5 minus 2.8 is less than 0. But let me go ahead and try it anyway. 0.5 minus 2.8 would be negative 2.3. Yeah, okay, so it says, yeah, it's going to be 0. The rule of thumb would say you go down 2 standard deviations, but since it can't be negative, it'll just want 0. Is it unusual for a car to have more than one bumper sticker? Well, it says the maximum usual value is 3.3, so okay. Let's actually look at the data again. If I look at the probability of one bumper sticker or more, that's like a 20% chance, so that's not bad. Oh, sorry, it's saying more than one. Yeah, more than one is still like a 10% chance. So, and does everybody see how you would get the probability of more than one bumper sticker is 1.06? All you do is you just go over here, say, hey, if I want more than one, that means 2 or more. So I go sum, but just start at the 2. Yeah. So the probability of at least 2 bumper stickers is 10%, which 5% in stats is usually what we kind of use. So it's like, it's more than 5%, that's not that unusual. Cool. All right, let's see if I can find the binomial stuff, because we did a couple of them like that last time. Okay, is it binomial? And okay, so randomly selecting 20 citizens of a state and recording their nationalities. So does that sound like it's binomial? Why not? Because 3 of them say no, right? So binomial, you have to have a repeated trial, which we have that because we've got all these people. We're picking 20, so it's like we're doing something 20 times. But what's the other thing you really need? Well, we would need to know the initial probability if we were going to compute it. But if we're just saying, okay, is this a binomial situation or not? What's the other thing we need? Okay, let me ask this. What do you need to know the initial probability of? Okay. Yeah, I mean, binomial distribution is where you're doing something and there's only two possible outcomes. I mean, you call one success and one failure most of the time. But it's like if you're talking nationalities, there's more than two answers we could get. So you can't just say, oh, I mean, if we reword this and saying, okay, we're selecting 20 citizens of a state and say, were they born in America? Then that would be binomial because yes, they were, no, they weren't. But if you're saying, were they born? No. So no, because there are more than two possible outcomes. Actually, it might be the last one because there's more than two possible outcomes and the trials are not independent either. So it's actually probably D. But I guess we'll wait and see. What does the independent thing mean while we're waiting for it to load? So remember, independent events means the result of one doesn't affect the result of the next one. So if we pick these 20 people, like imagine the whole state in a line, if we pick somebody out, put him back, and then picked another random person again, that would be independent because then the two choices have nothing to do with each other. But if I'm reading this right, where we pick someone out, then we pick someone else out, well, we can't pick that same guy out twice. So when we took the first guy out, we screwed up the probabilities just ever so slightly. Okay, I didn't expect it to take that long. You know any good stories, Ty? Not today. Oh, it just didn't do anything. I'm going to go ahead and change my answer. Since I think it's going to be the last one. Oh, no. Maybe it does just want B. Okay, yeah, it just wants B. Let's go to that 14. Okay. Is this binomial of, okay. So 500 voters are two political parties are randomly selected from the population of 3.5. As is she or she a member of A? What do y'all think? So there are two possible outcomes. Yep, there's two possible outcomes. Is the number of trials fixed? Yeah, I mean, we're doing 500 trials out of that many people. The probability of success is the same in all trials, and presumably there is some fixed number of people, so that's what is 5% of 3.5 million? I can't imagine I think it's got to be more than 500. Yeah. So I'm going to say yes. Make sure that's right. Yeah. So this not independent thing, again, that's going back to, well, if we took them and put them back, then they would be independent. They're really not independent as it is, but it's like you're talking 500 people out of 3.5 million. the difference you make when you take 1 or 10 or 20 or the first 499 out, it's not going to change the probabilities enough to really matter. So that's what they're saying. It's like as long as the sample size isn't at least 5%, then you can pretend like they're independent and it's going to be close enough.